we're going to look at Bayesian estimation. Okay, in the context of machine learning, this is going to be at the core of what is actually learning into machine learning. What we're going to see in the next module is that all the learning part in our model, whatever it's supervised learning, unsupervised learning, at the core of the learning procedure is going to be the Bayesian estimation. Okay, we're going to break that down in small pieces that are digestible and that we're going to see together. So the reference for this class is going to be the chapter 6 for the book from the class, Probabilistic Machine Learning for Civil Engineers. So let's start by an introductory example. So imagine we have a screening test for a super rare disease. So given we have that deadly disease, but so rare that only one human on Earth has it. So luckily we have a screening test for that disease, okay? But it's not a perfect test. So we assume that whenever we have a positive test, we can assume that the probability of having a positive test if someone has the disease is 0.999, okay? On the other hand, the probability of receiving a wrongful result, saying that we have a positive test, given that the person doesn't have the disease, it's 1 over 1,000, okay? So the question we can ask ourselves is that if you test positive, should you be worried? Okay? Here, if we want to look at this, we have to look at what is the prevalence of that disease in the population. And from the number I just gave you, here we have roughly 8 to the power 9, so 8 billion humans on it. And we say that only one of them has the disease. So here, given the quality of our test, we say, given the people that have no disease, the probability of still receiving a positive test is 1 every 1,000. So in that case, we have 1 every 1,000 tests. That's going to be a false positive times 8 billion humans. That makes roughly 8 million false diagnoses. We have 8 million false diagnoses, but we know that only one of them is truly affected by that disease. So the probability of having the disease, even if we have a test positive, I skip some steps and make some approximation here, but it's going to be roughly 1 over 8 million. So this is really tiny. If we compare that to the popular lottery here in Canada, which is 649, this is roughly like the same probability of buying 2 lottery tickets and winning the jackpot. So this is really, really unlikely. So in that case, even if you would test positive, there's absolutely no reason to be worried, just because the prevalence of the disease is so low that testing positive shouldn't affect at all your state of mind about whether or not you have the disease. So the message I wanted to convey to you here with this simple example is that if you want to properly extract and interpret information coming from data, you must not only consider that data itself, but also the probability for the quantity you're trying to reason with, okay? So this is key, and we can do this using Bayesian estimation, okay? This is what we're gonna walk through step by step together. So first part, we've seen the introduction here, why and in what context we're gonna use Bayesian estimation, but we're gonna dig into more detail about what is the basic formulation for the Bayes theorem. Then we're going to look at the first set of discrete cases. Then we're going to extend to continuous cases. Then, okay, we're going to see now that we can formulate our problem, we're going to have technical difficulty, notably with respect to calculating the evidence, okay, the normalization constants for our Bayes rule. And we're going to see the generic Monte Carlo methods through the importance sampling methods to see how can we address this challenge. And then we're going to extend to a third part of applications with respect to how can we apply Bayes' rule in order to learn the parameter of the PDF or a random variable. And this is going to be closely related to the learning part in machine learning that we're going to reuse in subsequent module. And finally, we're going to look at some analytical shortcut to doing Bayesian updating, because everything we're going to do here, we're going to see is computationally extremely demanding. Okay, that's what few people in real life in big deployment use machine learning. Why? Because it's computationally it can be really, really demanding, okay? But we're gonna see there are some really nice theoretical shortcuts that are not always applicable, but when applicable, make Bayesian estimation instant, okay? And this is what we're gonna see as the conjugate prior. So that put us in the first module where we're really gonna look into the machine learning basics. Here we're looking into Bayesian estimation, okay? And this is gonna be the core behind the learning for machine learning. So let's start by setting up the foundation for Bayesian estimation, and that comes through Bayes' rule. Then Bayes' rule has three main components. I would say even four main components. What we're looking for as the end result is going to be the posterior. Okay, this is what we're trying to obtain using Bayes' rule. But to obtain that posterior, we need three things: the prior knowledge for the quantity we're trying to quantify, the likelihood, how much weight our data or how much information my new data carries, and finally the evidence, also referred to as the normalization constant. So we're going to see how each of these things work and how do they play together. Okay, how do they come into play together? So why, in a general context, would we want to use Bayes' rule? Okay, it's when we want to apply it to contexts such as this. We want to infer the probability or the probability density for some unknown quantity given some other known quantity. Okay, here the known quantity are going to be our observations. Okay, either discrete or continuous, and we want to use this in order to modify or to update our current knowledge described by either a probability mass function in the discrete case or a probability density function in a continuous one for either a constant. So in a case where x, the thing we're looking at, is as a true value, okay, is an underlying deterministic quantity. We want to learn about what is going to be my current knowledge as described by a PDF or PMF for that deterministic quantity. Could be as well, what I'm trying to gain knowledge about is something that's intrinsically random. Okay, it's a random variable. In that case, what I'm going to try to do is to gain knowledge about theta, where theta are going to be the parameter describing the probability density function of that PDF. Okay, we're going to break that down in all those cases. So how do we retrieve Bayes' formulation from the definition of the conditional and joint probabilities? So here, let's assume we have two random variables, x and y, for which we both know their marginal PDF. So their joint PDF here is going to be obtained by taking the product of a conditional PDF times a marginal. So if I want to build my joint for x and y, there's two ways to do it. Either f of x given to y times f of y, so the conditional PDF of x given to y times the marginal PDF of y. Or equivalently, is going to be the conditional PDF of y given x times the marginal f of x. So in the general case, in terms of nomenclature for what we're going to see in this module, as well as all the following module, we assume that we know y, okay? Here, y is going to be our observation, but x is not, is our quantity of interest that we are trying to gain information about. So we don't have access to x directly. We cannot, for the various reasons, directly measure x, but we can measure y. And we know that x and y are dependent, and that dependent translates into that conditional probability, okay? In that case, we can employ Bayes' rule in order to make these two quantities equal, because these two quantities are what basically define that joint probability, okay? And given that I know y but not x, I'm looking at this thing. What is going to be the conditional probability of x given that I've observed y? So the only thing I have to do if I want to obtain Bayes' rule is to take that marginal and send it on the right hand side. So what I'm going to have on the left hand side here is going to be my posterior probability, or in this case probability density function, because I'm referring to lowercase f, so a PDF. So I'm looking for the posterior PDF of x given y, which is an observation. So in that case, I'm going to have my likelihood times my prior divided by my evidence or normalization constant. We're going to see that back in a few slides. So if we go with a little more formalism for Bayes' rule. So let's say we have a vector of random variable from x1 to xx. So from now on in these slides, the number of elements in a vector or in a set is going to be denoted by this kind of typewriter face font, okay? And if I'm referring to the x variable, that typewriter font with the same letter is going to represent the number of elements in either a vector or a set. So in that case, I have a vector of x random variable for which I know the PDF f of x. And I say I have a data set also that I've collected in somewhere, okay? Let's assume that I have a set of data. So calligraphic D is going to represent my set of observation, okay? My set of data. And here, I'm always going to assume that this calligraphic D is going to be my number of available observations, okay? So here I have a set of D observations, and these observations correspond to realization of the random vector Y, which has as many observations into it, okay? So that Y is also distributed following its own PDF f of Y. So in that case, our end goal with Bayes' rule is to do the following. Obtain the posterior PDF for the random vector x, given that I've observed that y equal to those realization d, which are actually realization of that random vector, okay? And this is going to give it given by the likelihood times the prior divided by the evidence, okay? Evidence or normalization constant. So I'm not going to represent y equal d, okay? I'm just going to make the shortcut of saying x given d, okay? This is going to be the formulation, the nomenclature I'm going to use from now on in the course. So when I say given d, it means conditional on the observed data, okay? These are actual deterministic quantity. So the posterior is going to be the likelihood times my prior knowledge as described by my prior PDF for the quantity x I'm trying to gain information on, divided by my evidence or normalization constant, okay? So let's break that down. Let's start with the prior knowledge, okay? F of x, given that x is the variable I'm trying to gain knowledge for, f of x is kind of my prior knowledge for what are the possible values that little x can take, okay? So this prior knowledge is subjective, okay? Or at least it's epistemic. It represents my prior knowledge, okay? It represents my knowledge about that quantity. So x in this case is a deterministic quantity. It's only that my knowledge is uncertain. So that's why I use a probability density, not to represent something that is intrinsically variable, but to represent something, to represent my knowledge of that quantity. So that prior knowledge can be based on either engineering heuristics, so prior knowledge for the phenomena I'm trying to study. It could base, in the case of sequential analysis, on the posterior obtained from previous data. So imagine that I collect a first set of observation. I obtain the posterior. That posterior could become my prior for a second set of data that would come in following the first set. And finally, it might happen in some cases that I have no prior information about what could be the prior, okay? I have no clue what's going on in that type of problem. In such a case, I could resort to using non-informative prior, okay, to reflect my absence of knowledge with respect to what could be the value x can take. So in all cases, I'm gonna describe my prior using either a probability mass function in the discrete case or a probability density function in the continuous case. So the second part of Bayes' rule is going to be my likelihood, okay? The likelihood described here, what is the probability or probability density of observing my set of data D given a specific value of x here, okay? So either I'm going to represent it in the long form y equal d, or in the short form just f of d given x, where here d assume always it's a set of specific deterministic value. Okay, these are going to be my fixed observation. So this is the likelihood of observing these specific observation given a value for x. Okay, So the n is going to be the conditional probability for my set of observation given all the possible values x can take. So note here that there's a special case that we need to consider. For instance, if we have exact observations, okay, meaning that whenever you're going to observe something, you're absolutely sure this is the reality. In such a case, we're going to say whenever your observation is actually the x you're trying to quantify, you don't need Bayes in that case, okay? Let's go back to the disease screening example we had in introduction, okay? If the conditional probability of receiving a positive test if you have the disease is equal to 1, and in the same way, the probability of receiving a negative test if you don't have the disease. So in that case, if your screening test is perfect, there's no point of using Bayes. Okay, why? Because when you're going to receive the information, when you're going to receive the observation, your prior doesn't play a role anymore because you know the ground truth, okay? Because in this case, if you had the disease, the probability of receiving a positive test is 1. It's a certainty. If you don't have the disease, you're going to receive a negative test. So it's going to be 1 as well. So in these kind of extreme case, whenever your observations are exactly the quantity you're trying to characterize, there's no point to use Bayes' rule. The observation you receive gives you all the information there is to know about this quantity. But stay vigilant, because this special case is really unlikely to happen in reality. In most cases, the observation doesn't represent the exact thing you're trying to characterize, okay? This is more the exception than the rule to have this context. So same thing here, I said that if the probability of test plus given disease is 1, the probability of having a negative test given disease is 0, and the opposite is also true. If you don't have the disease, the probability to having a positive test is 0 as well. So this is a perfect case that in most realistic contexts won't apply. But when it's applied, because the observation is exact, the prior wouldn't play a role, so there's no point applying Bayes' rule. Okay. The last part with Bayes' rule that we need to cover is the evidence. Okay, this is what's on the denominator. This is my prior probability of the data itself, or the marginal prior probability of the data. Okay, this is either called the evidence or the normalization constant, because this is what ensures that my posterior is going to integrate to 1 if I integrate with respect to x. So in the discrete case, if I sum my posterior with respect to all the possible x values, or in the continuous case, if I integrate my posterior with respect to x, in all cases, I should obtain 1, okay? Because this is by definition a probability density function. So if it wouldn't be the case, it means I got something wrong along my process. So in that case, in order to ensure that condition, we need to calculate our evidence or our normalization constant. This is what's on the denominator of Bayes' rule. And how do we calculate it? By simply integrating what's on the numerator of Bayes' rule. So in this case, we sum over all possible x, in a case where we have a discrete random variable x, of the likelihood times my prior. In the continuous case, where x is a continuous random variable, instead of summing, we're going to integrate what's on the numerator, so the likelihood times the prior. Okay, same thing in both cases. One is summation, the other is the integration. We're going to look at the first set of apply example of how can we use this Bayes' rule for learning about discrete random variables. Okay, we're going to review the disease screening context. Then we're going to look at the role of the prior in the context of fire alarm triggering. And finally, we're going to look at an example related to post-earthquake damage assessment. So let's look at a different disease screening example where assume that we have a population of individual. And we know from that population that the probability of having the disease is only 1%. Okay, we know in that population that 99% of the persons are healthy. Okay, we don't know who's healthy, who's not, but we know that 99% of them are healthy. Then we have a test. Okay, we receive a positive test. And we know that the conditional probability of receiving a positive test given you have the disease, is 80%. Okay? On the opposite, you have, if you don't have the disease, the probability of receiving a positive test, you know it's 10%. Okay? In that case, if we want to look at the posterior probability of having the disease if you receive a positive test, it's going to be the prior probability, so 1% times the likelihood, so this is my likelihood, so times 80%, divided by my normalization constant. So that same 1% times 80% plus the other branch I have here. So the prior probability for the other scenario, so the scenario of not having the disease, so 99%, times the likelihood of having a test positive if I don't have the disease, so 10%. So if I do these calculations, this is what's going to give me my posterior probability of carrying the disease if I receive a positive test. So if we put number of this, my posterior probability of having the disease if I have a positive test is, as we discussed, the likelihood of a positive test given the disease times my prior probability of the disease, divided by my normalization constant. So here, 1 times 80% divided by the same thing, plus 99% times 10%. Result, 7.5%. If I want to obtain my posterior probability for the other alternative, not having the disease, given that I receive a positive test, the denominator here remains the same thing, but I replace what I add here, which is the same as here, by what I'm going to have on my second possibility. So the other side of my branch here, the probability of testing plus given no disease times probability of no disease. In this case, 92.5. So note, if we sum 92.5 plus 7.5, we're going to get 1, okay? Because my posterior probability over all possibilities must always be 1. Note a little thing. Here, my likelihood, okay? The likelihood of testing positive given the two cases is not a probability density, okay? Or it's not a probability here, it's a likelihood. So that's why these likelihood doesn't have to sum to 1. However, my posterior probability must sum to 1. So always keep that in mind. Likelihood doesn't sum to 1, probability sums to 1. So let's look at an example that I commonly do when I'm doing presentation, okay, to explain the role of prior in reasoning. Okay, I've done it dozens of times, sometimes in front of hundreds of people, and I always have the same behavior. So what I typically do, I take my phone, I get it out of my pocket while I'm talking, okay? I'm interrupting the talk. I'm saying, hey, I'm receiving a tweet. There's a fire in the building. We need to evacuate. So what I get when I say this is all kind of strange faces of people who are kind of puzzled, questioning themselves and asking, what is he talking about? But never in the dozens of times I've done this example, I add anyone stand up and evacuate the room, okay? But this is weird because you have someone that tells you the information and I try to look convincing. There's a fire, you guys need to evacuate and no one evacuate. Why is this? Okay, how can we explain this behavior? This is what we're going to look at together here. So at the moment where I was giving this information to the audience, there's two possibilities. Either everything is fine, business as usual, or there's a fire. And at time t, you have me telling the information to the audience that there's a fire, okay? So here, it's a build-up example. We can assign the likelihood of receiving this information, given that there's a fire, it's 0.95, versus the likelihood of receiving this information if everything is fine. It's much lower, it's, let's say, 5%. But given this, why no one never react? It's because, actually, before receiving the information, everyone has a really strong prior information that fires are really unlikely event. So despite the fact that it's a lot more likely that someone is going to tell you there's a fire if there's an actual fire, my prior knowledge of the fire tells me something else. So we can assume that right before I gave that information, let's say 1 minute before, the general audience had that prior knowledge that the probability that everything is fine, it's let's say 0.99 versus 1% probability that there's a fire. What happened in between? We can assume that there's some transition probability, okay? Things might change. So if everything was fine, there's a 0.99 probability that everything is still fine. There's a 1% chance that the fire started, okay? On the other hand, if there was a fire just before I gave the information, it's a certainty that that fire went on and carried on. So in that case, what we want to do is to combine the information from my prior knowledge, the transition probabilities, as well as the information I gave to the audience to calculate at time t what were their posterior knowledge of there's a fire in the room. So in that case, if we do that calculation, it's going to be 70% probability that everything is fine versus 30% probability that there's a fire. So despite the fact that someone tells that there's a fire, here everyone is going to be believing that everything is fine. And notice whenever there's an alarm trigger in a public building, people tend not to react or react really, really slowly. Why? Because they all assume that fires are extremely rare event and that it's much more likely to be a bug or a problem with the alarm or either a test drill than being a rightful alarm. Okay, so that explains the slow responses of people when they're reactive. And here, don't get me wrong, no one ever do these calculations in their heads. Okay, so here I'm not trying to argue that people are doing that Bayesian updating in their head. Here, it's a simple way of rather modeling their cognitive behavior. Okay, people are not thinking this way, but we can build that simple mathematical model to explain their behavior. So what we're going to do, we're going to break down this example to see how can we calculate that 0.7 and that 0.3. But before this, what do you think would happen if after I gave that information to the audience that I receive a tweet, there's a fire. So at time t plus 1, what if a second independent person would have come into the room and tell the audience the same thing? I'm pretty sure that at time t plus 1, after I gave the information, the second one tells the same information, everyone would have rushed through the door. And if we look at the probability at time t plus 1 of receiving the two information, we have a 90% probability for a fire, 10% for everything is fine. Okay, so we're going to see how we can break that problem in little chunks that are easier to understand. So we start with defining what is our state variable. Okay, my state variable is either there's a fire or there's no fire. Okay, I didn't mention it, but this check symbol is the negation symbol. So fire and no fire. Okay, so here in order to facilitate following my example, I'm not going to use these variable. I'm going to use these symbol. Okay, fire and no fire, everything is fine. So my observation, what is it? My Y is going to be either an alarm or no alarm. Okay, rather than saying that I'm giving the information, we're going to assume that, for instance, the alarm rings. Okay, so alarm or no alarm. So we're going to look at what is the likelihood in this problem. The likelihood is these 0.95 and 0.05. So what is the likelihood of an alarm given the state? So the likelihood of receiving an alarm if there is a fire is 0.95. The likelihood of receiving an alarm if everything is fine, so a false alarm, is much lower, let's say 5%. What is my prior knowledge? We say that the prior knowledge of a fire at time t minus 1 was 1%. Prior probability of everything was fine was 0.99. And we define some transition probabilities. What is the probability at time t of everything being fine? If at time t minus 1, everything was fine. We said it's 0.99. What is the probability of having a fire if everything was fine before? We said it's 1%. What is the probability of having a fire at time t if at time t minus 1 it was a fire? It's 1. And the probability of everything is fine if there was a fire, we define it as 0. Okay, so here we have all our possible transition between the state over time. Now let's combine all this together. So going from t minus 1 to t, we have 4, but really 3 possibilities because this one we know the probability is 0. So what we want to do, the first thing, is to compute our joint probability. Okay, for what is the probability of each pair of states. So being at the same time at having a fire at t minus 1 and still having a fire at time t. Okay, so that joint is going to be obtained by the product of a conditional and a marginal. Okay, my conditional probability of having a fire at t, given that I had a fire at t minus 1, times the marginal probability of having a fire at time t minus 1. Here, I want to look at all my possible combination for my joint knowledge. So in this case, it's going to be prior probability here, or my conditional probability of a fire given a fire, it's 1 times prior probability 0.01, okay? So my joint probability is 0.01. What is my joint probability for having a fire at T and be okay at T minus 1? So it's going to be that conditional probability here, so 0.01 times my prior probability, 0.99. So result 0.0099. My third possibility is, in this case, being fine at T and being fine at T minus 1. So it's going to be 0.99 times 0.99. So in this case, 0.9801. And my last possibility, I'm fine at T, but there was a fire at T minus 1. Okay, we know this length is 0, so the probability is going to be 0. Perfect. But I'm not at the end interested into those joint probability, okay? What I want is to gain my prior knowledge at time T, irrespective of what I was in time T minus 1. How do I do this? I'm going to marginalize, meaning I'm going to sum over the state at time T minus 1. So in that case, to obtain my marginal probability of having a fire at time T, I'm just going to sum the two possibilities that were considering the probability of having a fire at time T. So in that case, 0.0099 plus 0.001 is going to give me 0.0199. I do the same thing for being fine. The sum of those two joint probabilities, 0.9801, okay? And that represented 0.98 and 0.02 I presented to you earlier. But this is only my prior probability, okay? This is not yet my posterior probability. In order to have my posterior probability, I have to include the information, okay, of, for instance, the alarm ringing or someone giving the information that there's a fire, okay? So now to obtain that posterior probability, given the information provided by, say, an alarm ringing, is going to be the conditional probability of the alarm ringing given a fire. So this is my likelihood times my marginal prior probability that there's a fire at time T, divided by my normalization constant, meaning the same possibility I have on the numerator here, plus the other possibility, meaning that the alarm ring given that everything is fine, time prior probability that everything is fine. So in this case here, what we have on the numerator is going to be the joint probability of having an alarm and a fire simultaneously. And what we have on the denominator is going to be my marginal probability of having an alarm. Okay, this is my evidence or my normalization constant. So if we put we fill in the numbers, what we're going to get is 0.28. Okay, and the complement, if I want to have the other possibility, instead of being a fire, probability that everything is fine, given that I have an alarm that is triggered, is going to be 1 minus 0.28, so 72%. Okay, so you see here, how can we combine the prior knowledge, in this case transition probability, with evidences or with observation in order to compute our posterior knowledge. So let's consider a second example, okay, or more a third example, where we want to look at post-earthquake damage assessment, okay? We have a random variable x such that the possible outcome for that random variable belongs to either the description light, moderate, or important, okay, to describe the intensity of an earthquake. So these are here mutually exclusive, collectively exhaustive events, okay? Then y is going to be my observation. So y is going to correspond to the state of a structure, okay? Either being damaged or undamaged. And we can see that if I have my sampling space here, I have my 3 MECE events, so the intensity of the earthquake, and the event damage and undamaged are also additional events that can happen on top of that Venn diagram. We have additional information such as we know what is the conditional probability of observing damage given each building intensity, each earthquake intensity, okay? Low, moderate, or high. So the probability of observing damage if the intensity is low is 0.01. The probability of observing damage if the intensity is moderate is 10%. The probability of observing damage if the intensity is important is 60%. And I have also my prior probability of damage intensity. So in this case, my probability for low intensity, 90%. So low intensity earthquake are much more likely than high intensity earthquake. Probability for moderate intensity is 8%. Probability for high intensity is 2%. And at the end, notice how for the prior probability, if I sum these probability, the sum is equal to 1 because this is a probability mass function, okay? Probability must sum to 1. This is my likelihood, okay? If I sum this likelihood, it doesn't have to equate to 1 because this is a probability density. This is a likelihood, okay? Probability sum to 1, likelihood don't have to. So at the end, what I'm trying to quantify here is going to be what's going to be my posterior probability for X given that I have observed Y, okay? Given I observed that there are some damage building. So in that case, it's going to be my likelihood times my prior probability divided by my evidence, okay? How do we calculate this? We're going to do it step by step. First step is going to be to calculate my evidence here, okay? So I'm going to compute the evidence by summing everything I have on my numerator. Namely, here is going to be my joint probability for my observation is there's damage and the intensity is low. So conditional probability of damage given low intensity times probability of low intensity. Same thing for moderate, same thing for intense earthquake intensity. So in that case, if I fill in the number, I'm going to get 0.029, okay, for my probability of having damage, my prior marginal probability of having damage. Then my posterior probability of having an intense earthquake, given that I have observed damage, is going to be my likelihood of having damage given my important earthquake intensity times prior probability of earthquake intensity divided by the normalization constant or evidence I just calculated here. So if I fill in the number, I'm going to get 41% of having important intensity earthquake. For the moderate earthquake, I'm going to have 28%. For the light intensity earthquake, 31%. So, okay. So the prior probability of having an important intensity earthquake, my prior knowledge was only 2%. But after observing that there's actual damage on my buildings, that posterior probability increased from 2% to 41%. Okay? So at the end, I want you to see that reasoning requires considering both the prior knowledge for the quantity you're looking at, as well as the information carried by your observation. And this is always done the same way using Bayes' rule. Okay, so now let's switch to another context. We're going to look at how can we use the same Bayes' rule, but not anymore in a case of discrete random variable, in the case of a continuous random variable, okay? So we're going to look again the likelihood, evidence, and posterior. So the main difference between discrete and continuous case is going to be in the definition of my likelihood function. Okay, f of d given x, which is now a probability density function. So again, as before, whenever my observation is perfect to describe the quantity I'm trying to characterize, we don't need Bayes' rule, okay? Because here, the likelihood is going to be equal to my prior, which is to say that my posterior PDF for my for my quantity I'm trying to quantify is going to be a Dirac delta for my actual observation, okay? A Dirac delta is all the probability content concentrated on a single value, okay? So in this case, I'm representing the true value with x with a little at in the reverse here, okay? So what I want to say here is that in all the contexts we're looking so far, there's an underlying truth. That underlying truth is that x at, okay? There's a deterministic constant that represents the true state of the world, okay? we represent our knowledge of that thing with a probability density function, or before with a probability mass function. But that thing is not representing the variability in that underlying truth, okay? It represents my uncertain knowledge about what the value this quantity may take, okay? But in the case where we have an exact observation, and that observation is equal to the underlying quantity I'm looking at, it means whenever I'm going to collect that observation, I know exactly what the underlying state of the world is. So in that case, don't need Bayes because the prior won't play a role. But again, as it was before, this is more the exception than the rule in practical case you're going to face in engineering. So the question we're trying to answer is, given the true value for the state of the world, how can we characterize our knowledge of what are the values that X can take? So, and to do this, what we have access to is imprecise observation of that true quantity. So we might have different types of observation. We're going to look at 3 types of observation here. The first one is a direct observation. So we're going to assume that Y, the quantity we're observing, is not directly X, okay? It's not the truth. It's going to be the true value plus V, where V describes an observation error associated with our process of collecting the information. It might be if we're using a sensor to measure a quantity, a physical quantity. That sensor is not perfect, okay? It's going to have, for instance, electronic noise associated with the measurement. So the value returned by that instrument is going to be the true quantity plus a perturbation, so an observation error, added by the physical process of measuring the quantity. So this is the case for a direct observation. We not only have the case of direct observation, we could also have a lower bound or censored observation. In such a case, we know that the data we're obtaining is actually a lower bound for the reality. Imagine you're trying to measure the temperature, okay, of a specimen for something that is really hot. But the only thing you have access to is a thermometer that works in the range from minus 40 degrees Celsius to plus 40 degrees Celsius, okay? Whenever you measure above 40 degrees Celsius, it just tells you, I can measure higher than this temperature. So in that case, if you're trying to measure something that is actually has a temperature above 40 degrees Celsius, you won't know exactly what's that temperature. The only thing you will know is that you cap the capacity of your thermometer, okay? So in that case, the information you're gonna have is that the actual temperature is somewhere above 40 degrees Celsius because you've eliminated all the temperature below this one. It could be also not only a lower bound, could be an upper bound. So in the case where we want to do, for instance, lab experiments, okay? In order to characterize, say, the concentration of contaminant in solution. In that case, we have what we actually call detection limit, okay? If the concentration is above a given limit, the machine is going to tell you, I don't detect anything, okay? But don't detect anything doesn't mean you don't have any contaminant. It's just that it's below the detection limit of the machine. So in that case, whenever you record nothing, you don't record 0. You just know you're below the detection limit of the machine. So it can be anything between 0 and the detection limit. And in all cases, that V represents the observation error. And here, to keep it simple, we're going to assume that our observation error is going to be modeled by a random variable, which follows a normal distribution with mean 0 and variance sigma V squared, okay? This is not a strict rule, it has to follow this. But here, in order to keep things simple, we're going to make that simplifying assumption. For your cases, you might have more complex observation process. You need to take it into account. So here, V is going to be a 0 mean Gaussian observation error. And we assume that for all the different observation we do, all the observation error are independent of each other. So Vi and Vj are statistically independent for any I not equal to j. So given this information, how can we define our likelihood? So the likelihood of an observation given the true state of the world. So in that case, we're going to quantify the likelihood for an observation Y1 for this additive observation process. So here my likelihood, so the probability of observing y, given that the state of the world is x, I can either represent it like this. Some references are going to represent it like this, okay? Likelihood of x given y. But no matter how you represent, you should always consider that this is the conditional probability of observing a given value given my state of the world x. And in this case, if we assume that x at is a constant and v is a random variable, this likelihood is going to be modeled by a normal random variable where I'm going to sum v and a constant x. So basically it's going to become a normal with expected value x and variance sigma v squared, okay? Because x at is a deterministic quantity. So if I write down the analytical formulation for that PDF, it's going to be my normal PDF with expected value x and variance sigma v squared. And if I plot this PDF, okay, I'm going to plot this PDF with respect to both x and y, okay? This is what we see here, my joint PDF with respect to both x and y, okay? But in practice, I don't have x and y that are really variable, okay? If I plot this PDF with respect to y for a given x, okay, because this is the native formulation for my likelihood. It's what is the prior probability of observing y, or in this case, probability density, because the quantity is continuous. What is my prior probability density of observing given y, given x equal a specific value? So in this case, I plot for x equals 0. So this is my pink line here. So this would represent what my likelihood would look like, okay? What is the likelihood of observing any value y given x equals 0? But in our case here, we're going to have a specific observation. So the specific observation would be -1, okay? So in this case, what was the likelihood of observing y equal -1 if x equals 0? I go on this PDF and read the PDF value. So that would be my likelihood of observing y equal -1 given x equals 0, okay? But it's not only x equals 0 that is possible. It's all possible values of x. So if I slide this slice over all possible values of x, and I read the value here, what I would obtain is the curve in red here, which is equivalent of looking on this 2D figure, this 2D surface, and taking that red slice here. So plotting for all possible values of x, and the value equivalent to my observation, y equal -1. This is what we have in the red curve here. So for all possible values of x, what was the likelihood of observing y equal -1? Okay, this is the interpretation of what's my likelihood. So this was the likelihood if I had direct observation. What if I have an lower bound observation, meaning that my observation is smaller than the actual quantity? Okay, if I have lower bound observation, my likelihood is going to be actually the integral of my PDF I defined previously. So in that case, I'm going to integrate from y to plus infinity. So this is equivalent to the complement of the CDF of what we had before. And the formulation for the CDF is given here, so that if I plot this relation with respect to both x and y, it's going to look like this surface here. So if I look at my likelihood of any y given a specific value of x equals 0, it would be like extracting that pink line out of that surface. Okay, for a specific value of x, give me the likelihood of any value y. But in practice, this is the inverse we're going to look at. We know y because we've observed it. So here what we do, we plot instead with respect to x. Okay, so for a y equal -1, my actual observation, what would be the likelihood of, what would be the likelihood of what is the likelihood of my observation y equal -1 given all possible values of x? Okay, this is how we should formulate it. And this is what's represented here. So if I know that my actual observation is -1, what was the likelihood of having that -1 given all possible different values of x? So we say that here it's unlikely to have the observation -1 if the x values were actually really small. we have here a large value, a large likelihood of having y equal -1 if x was really large, okay? And here, if we change sigma v, if we make it to 0, this curve is going to look like a sharp jump. If we make it large, it's going to look like a smooth transition. Same here. If we make sigma v really small, this is going to sharpen that peak you see here. If we make it really large, it's going to dampen it, make it really flat, make it really wide. So the third case we can look at is the complement of this one. Instead of being in a lower bound, it's going to be an upper bound. So in that case, if it's an upper bound, instead of being in the complement of the CDF, it's going to be directly the CDF. Where if we represent it, now the relationship is inverted, okay? What is the, if my observation is y equal -1, okay, so if my observation is y equal -1, the likelihood of having y equal -1, given all possible values of x, is going to be really high for a low value of x, because I'm talking about an upper bound observation, and it becomes really low for I values of x. So now we look at how can we define the likelihood for any one observation individually. But in practice, it's going to be really common to have a bunch of observations at the same time. And then what we need to do is to define what is going to be my joint likelihood, okay? In the case where we assume that we have an additive error process as we formulated earlier, and we have some VI and VJs, which are observation error for two different observations. And if we assume that these observation error are statistically independent from each other, we can assume that my joint likelihood for my set of observation, conditional on the values of x, is going to be obtained by the product of the marginal likelihood, okay? As we've seen in the module 1b, where we've reviewed probability theory, we can build a joint PDF or a joint PMF by the product of the marginal PDF if these random variables are statistically independent from each other. And given the statistical independence assumption for the observation error, we build the joint from the product of the margin. But here there's an issue. The PDF for y equal a given value given the x is typically going to be much smaller than 1. What happened here if we take the product over d, which can be 10, 100, 1,000 observation, for many quantities that are lesser than 1. So really quickly, we're going to reach 0, okay? Just by a rounding error in the machine, we're going to have a 0 underflow issue, which is that we're going to get 0 even if the real quantity is not really 0. So if we want to get around this difficulty, what we could do is instead of taking the product of quantities that are smaller than 1, we're going to take the sum of the log of the marginal likelihood. Okay, by doing this, by summing the log of quantity rather than taking the product, and at the end, making the exponential of the sum of the two things here, we're going to go around the difficulty of a numerical underflow while taking the product of many small quantities. So at the end, keep in mind, you should always use this formulation here. That's going to be numerically much more robust than taking the product here, and is going to be equivalent in any point. The last thing we want to look at is the evidence, okay? What we want to do here is to calculate the normalization constant for our Bayes equation, okay? So in this case, we're going to take, since we're continuous, we want to take the integral of the likelihood times the prior, okay? In most practical case, we won't be able to perform that integral analytically, okay? So we have to resort to approximate formulation to do this. And we're going to look at a first crude rule or a first crude method of how can we perform that integration. And this is the most basic one, the rectangle rule, okay? In this case, what we're going to do, we're going to discretize here our PDF, representing the product of the likelihood and the prior, into some bins, okay? And for each bin, we're going to evaluate the height of the curve. And by summing the area under each bin, this is going to represent the result of my integral. So if I divide my domain here in 7 bins, which all have a width of 10, because this is my range here over 7 bins, I can approximate my normalization constant, the result of that integral, by the sum of each bin times the height of my discretized domain, okay? In this case, 0.2158. But here you can assume I'm going to make a lot of mistake. What if I increase my number of bins to 10, okay? 2158, 2198, 10, okay? What if 20? What if hundreds? Okay. We see that as we increase the number of bins, we converge to a steady solution that is closer and closer to reality, okay? But here, don't get too excited. Here, this approach works really well in 1D, but we're going to see in a couple of slides from now that we cannot scale that approach to complex problem, okay? And this is a big limitation. So, okay, so let's look at the posterior PDF for X given some data D, okay? So now let's assume we have 2 observations. First observation is y equal -1. The second observation is y2 equals 0. So here, y, my observation, is equal to the reality plus v in observation error, okay? Where v, my observation error, is a realization from my random variable v, which represents my observation process, which has 0 mean and variance 1, okay? And my prior knowledge for x, the quantity I'm trying to characterize, is going to be described by a uniform distribution in the range -5 to 5. So my question, what is going to be my posterior f of x given d? So in this case, my posterior is going to be the product of the likelihood of observing d given the possible values of x, times probability of x divided by normalization constant, okay? In this case, in the previous example with the rectangle rule, I already calculated what was my probability, okay? So in that case, it's 0.2197. So if I represent my prior here, uniform in the range -5, 5, my likelihood, okay, my likelihood is going to be normal with mean equal to my x, so my observation x, my true quantity x, and variance 1 square. If I take the product of both, this is going to give me my posterior if I divide by 0.2197, okay? So here it looks really simple because I can do all of this analytically. But in most practical case, I cannot do it, okay, for many reasons. One of them is that calculating that evidence, that normalization constant, is really, really hard. Doing that integral in 1 dimension is feasible. But as the number of dimension is going to increase, this is going to become harder and harder, okay? So using the rectangle rules, as we've seen, it's not at all scalable. This is really limited to either 1D or 2D problem. What I wanted to show you by doing this is conceptually what we want to do, but we need to see more advanced method to achieve our goal. Because here, as the number of dimension increase, so the number of parameter we're trying to do inference for increase, it's just not going to work. In this case, the first method we're going to see to achieve this is Monte Carlo sampling, okay? We're going to see in this module our first introduction to simple Monte Carlo sampling through importance sampling. And in the next module, so module 4, we're going to see next, we're going to see more advanced sampling through MCMC, Markov chain Monte Carlo, okay? But for now, let's lay the foundation work in order to be able to see this next. So what is Monte Carlo sampling? Okay, we're going to explore this through an example. What we want to do is to use sampling in order to calculate what is the area of this circle that is inscribed in that unit length square, okay? So in this case, I have a circle that has a diameter of 1 unit, so radius of 0.5. This is the equation of that circle. So what we have to do first, if we want to use Monte Carlo, is to define an indicator function, okay? indicator function is function of x and y, my lateral and vertical coordinates. So that indicator function is going to take the value 1 if I'm inside the circle and 0 if I'm outside. Okay, this is the only thing that my indicator function return, either 0 if I'm outside, 1 if I'm inside the circle. And I can define my area for that circle as the integral over my all x and y of the product of my indicator function, which is going to take the value 0 and 1, times my probability of being anywhere in my space x and y, where I'm going to assume that my probability here is uniform over that square. So in that case, this integral, if we remember what we saw when we did the revision for probability theory, this is equivalent to saying this is an expectation. Okay, I'm trying here to calculate the expected value of my indicator function for both x and y, which are now random variables. Okay, so the question is, what is the area of my circle? So what I'm going to do, I'm going to take samples, okay, in my uniform distribution for the possible position x and y. So I assume that I can be anywhere with uniform probability in the space x and y. So my joint probability for x and y is constant, is equal to 1. So in that case, I want to generate samples that are uniformly distributed, and I want to evaluate what is that indicator function for each of those samples. So here I can say that my area is going to be defined by the expectation of my identity function. So in that case, the expectation is 1 over s, my number of samples I'm going to take, as the number of samples tends to infinity, of the sum of my indicator function for each of my samples. So the samples that are red are going to be inside my circle, the green would have been outside. So all the red are 1s, all the greens are 0s. In practice, I never have access to an infinite amount of samples. So instead of being exact, I'm going to put an at on top of it to say this is an approximation. This is an estimator. So in that case, it's going to be 1 over s, where s is lesser than infinity, of the sum of either 1 and 0, depending where is the point landing. So in that case, I have taken 100 samples. Okay, for 100 samples, my expected value is 0.8, meaning that I have 80 red points with value 1, for which the indicator function is 1, and I have 20 green points for which the value of the indicator function is 0. The real value, because we know actually what is the formula to calculate the area of a circle, is going to be 0.785. Okay, we're not spot on yet. What can we do? Increase the number of samples. If instead of taking 100 samples, I take 1,000 samples. So in this case, the reality is 0.0785. My estimation is 0.759. So I'm getting closer to reality. If I take 10,000, we see that we're really tending towards reality. Okay? So here, what we have to keep in mind is that the quality of our estimation, for in this case, the area of the circle, but any expectation in general, depends only on the number of samples, or at least in this case, depends on the number of samples, and is going to be independent of the number of dimensions. Okay, this is what allows to scale Monte Carlo problem or Monte Carlo estimation to larger dimensions. Okay, because it's only dependent on the number of samples, not of the number of dimensions. There are other things that kicks in when we have more dimension, but here we can see that mathematically it's independent of the number of dimensions. And you can see Monte Carlo as simply a generic numerical integration methods, okay? That is way more powerful than that rectangle rule we see. That is barely never applicable. So how can we calculate our evidence, which is at the end an integral, as we've seen in this case? So the evidence is going to be the integral of the product for my likelihood times my prior, okay? So this is equivalent of the expectation of my likelihood, okay? Keep in mind, an expectation is the weighted sum of an outcome times its probability of occurrence, okay? So this is the probability of occurrence, this is the outcome, Okay, so this is why we can say this is the expectation of the outcome. So here, if I want to approximate that normalization constant, I'm going to sum the product of the likelihood times the probability of my samples. The probability of my realization divided by my sampling distribution. Okay, where XS correspond to what is the distribution I took my sample from. So in this case, if I take the special case where I take my samples from my prior knowledge for XS, these two are going to cancel out, and I'm going to be left to my normalization constant is simply 1 over my number of sample times the sum of the likelihood for each of my sample XS. Okay, S is the index for my samples. And this is true if I draw my samples. So these are realization from my prior knowledge. But be careful here. When you apply this, there's some limitation. Okay, with Monte Carlo integration like this, if you take your sample from the prior and the prior is really broad in comparison with your likelihood, this is going to be theoretically correct, but it's going to be highly inefficient. Why? Because you're going to take samples in a really broad prior, whereas you're going to want to sample in that narrow likelihood. Okay, so you're going to be likely to waste a lot of samples in region of your domain that contain a very low probability content. So this is going to be theoretically correct, but highly inefficient. Okay, so what we want to obtain is that posterior, but that posterior in most cases is not going to have an analytically tractable closed form solution. So what we can do instead is to simply represent that posterior by its summary statistics. So the posterior expected value, which is going to be the outcome of X times its posterior density. Okay, we want to integrate over all possible density. Or same thing for the variance, X minus the expected value squared. This is the definition of the variance weighted by the posterior PDF as well. So how can we do this? Using Monte Carlo sampling. Okay, so our posterior expected value is going to be 1 over S, number of sample, the sum over all my realization of the value of the sample times the likelihood obtained when using the sample times what was the probability of the sample divided by my normalization constant that we defined previously, divided by my sampling density. If my sampling density here is my prior knowledge, these two terms cancel, and I have this simpler formulation. Same thing for the variance, where I replace XS by XS minus the expected value that will be approximated here, square. Okay, and at the end, the same thing here. If I sample from my prior, these two terms cancel out, and I have this formulation. So we said before, first thing we see here, what's happening when as the number of data available increases. Okay, as my number of data point increases, what's going to happen is that my posterior is going to converge to a Dirac. Okay, what it means is as my number of independent observation tend to infinity, then my posterior is going to converge to a single point that is aligned with what was the true state of the world I was trying to analyze. Okay, so my posterior PDF here converged to a Dirac, so all the probability content on a single value that is centered on the true value. And this is true only when the number of independent observations tend to infinity. Okay, keep that in mind, because if you have dependency in your data, you might get an infinite amount of data and not get that behavior. For instance, imagine that I have one data point and I just replicate the value and analyze it. Okay, in this case, having one data point or 1,000 data points, since it's just replicated data, it doesn't carry more information. Okay, for gaining information, you need to have multiple independent point of view, multiple independent observations. And again, this is only applicable for identifiable problem. We're going to come back to this. So basically converging to a Dirac, what does it imply? It means that the expected value for my posterior is going to converge to the true value, and the variance is going to tend to 0, okay? And again, as I said, this is going to happen for identifiable problem. What is an identifiable problem? Let's look at this. So what happened in case where the amount of data increase, but we have a non-identifiable problem? So let's imagine that we want to characterize the contaminant concentration in a stream, okay? But we cannot measure anywhere in the stream. That stream is the result of two other streams merging, okay? So we have two streams, X1 and X2, where they each can have their own contaminant concentration. And I have access to one observation yi, which is only available after those two streams merge together, okay? So my observation yi is the sum of x1 plus x2 plus v, which is my observation error, which has 0 mean and variance 2 square, okay? So, and this output is, that observation is only available at the output of both streams. Here I assume that I have a uniform prior knowledge. So this is, it means proportional. So it's proportional to a constant. So it means uniform prior knowledge over my entire range of x1 and x2. So my question is, what is my posterior knowledge for x? So if we draw here my posterior, it looks like this. So this is x1. What is the possible concentration contaminant in my first stream? This is x2, my concentration contaminant in my second stream, okay? If I have access to a single observation d equal 1, this is my posterior. So my observation is 25.1. But here you need to imagine, since my observation comes after both streams have merged, I cannot distinguish from what is the concentration for the first or the second stream, okay? So this is problematic here. This is what we call a non-identifiable problem. Because here, the true value is where I've put the red cross, okay? Because here, this is a synthetic data. I assume this is my reality. But you see that my posterior knowledge looks like a ridge, where any value on top of that ridge are equally likely, meaning that I could either have a high concentration of contaminant in stream 1 with a low in x2, or the opposite, a high concentration in x2 and low in x1. And both would be equally good at explaining my observation of 25.8. What happens if I increase my data? That ridge is just going to become more and more concentrated. But any value here on that ridge, there are infinitely many possible combinations of x1 and x2 that are equally well explaining my observations, okay? So here, what would happen if instead of using a uniform prior, I would have used a more informative prior, such as a normal distribution. In that case, that would solve my identifiability issue by regularizing my problem and making it identifiable, okay? So in summary, we saw how we can use Monte Carlo sampling in order to evaluate our normalization constant, or posterior expected value, or posterior variance, okay? And keep in mind, this works, but this has some limitation in the case where we're taking samples from my prior, which is diffuse, and where my likelihood is sharp, okay? Why? Because I'm gonna take a lot of samples here in the prior, and few of them is gonna end up in that high probability region. So my estimate for my normalization constant is highly likely to be poor, meaning I would need a lot of samples to have an accurate calculation. Okay, so let's look at an example of application of this for the concentration, the estimation of a contaminant concentration in lab experiment. So, okay, we have a laboratory test for measuring the concentration in mercury, where the observation we have is going to be a direct observation, so the true quantity plus an observation error. If we're above the detection limit of 10 microgram per liter, or we're going to return an error if we're below the detection limit, okay? Where here my V, my error, is a realization from that normal observation error, okay? So normal PDF means 0, variance 2 squared. So here, what the question we're trying to answer was the posterior PDF describing the concentration given my observation, which is an error, okay? The machine tells me you're below your detection limit, okay? And we're gonna look at this case for two scenarios. The first one, my prior is a uniform PDF in the range 0-50. And the second one, I'm gonna assume I have prior knowledge where described by a normal distribution, expected value 25, variance 10 squared, okay? So this is my prior for my first case. This is my likelihood describing an upper bound observation because this is my detection limit. And each dot you see here are my samples taken from my prior distribution, so my uniform distribution, in order to calculate my normalization constant. And this is my posterior. So the product of prior, likelihood divided by normalization constant. Versus, why would I obtain? If I take the samples from my prior. You see that my prior are a lot more concentrated around here than they were there. Okay, so we see that already in my high probability content region, I'm gonna have way less samples. And this gives me my posterior. So what I wanted to show you here is that even if we have censored observation, we can leverage Bayesian estimation in order to extract information that was available to us. Okay, in this case, my normalization constant here is going to be obtained by 1 over S, number of samples, the sum of the likelihood for each respective sample for XS, taken from here to prior. So in this case, 0.067. And here I have only one observations. So here I don't need to take the product. I can directly evaluate my likelihood for my single observation. Same thing for calculating my posterior expected value, posterior variance, okay? So if I do calculation, my posterior expected variance for this, 6.27, variance 17.96. Okay, so what would happen if instead of having a single observation, that is a censored observation, I would have direct observations that are all above the detection limit. So these would be the 100 different possible values. And I have my prior knowledge, which is uniform. So in that case, this is my prior, this is my likelihood, and the points you see there are my samples that I've used to calculate my normalization constant, my evidence. So what you see here is that none of these points lie in that high probability region. So what does it mean? So the more data I have, the more peak is going to be my likelihood because it's going to be the product of several likelihoods. So I think the product is going to concentrate my information. So in that case, my normalization constant, the true value that I obtained by using millions of samples is approximately 1.19 times 10 to the power minus 78. And if I use 50 samples as represented here, it's going to be to the power of 983. So there's a factor almost 5,000 between these two estimates. And that's going to lead to a really poor posterior and poor posterior estimate. So there are two solutions, either to prop up the number of samples. In large scale cases, it's not going to be viable. So we cannot just rely on sampling, taking more samples because there's a cost associated with samples and with large problem it becomes prohibitive. So instead, what we're going to see in module 4 in the next module is how can we overcome these limitations using MCMC, Markov chain Monte Carlo. Okay, so now we're going to look at another context where we're trying to quantify the posterior for the PDF of parameters. Okay, so we're going to, in all the contexts we looked before, we assume that X, the variable we were trying to quantify, is deterministic. Okay, now we're going to push that forward saying this is not only a deterministic quantity, this is going to be a random variable. So now we're trying to use Bayes' rule in order to characterize what are the parameters of the PDF describing that random variable, okay? And this is really what we're going to be building on when later on we're going to build our machine learning models. So we're going to detail the context of that scenario. Then we're going to define the prior knowledge for our parameters, the likelihood, the posterior, and we're going to introduce a new notion, the one of posterior predictive. Okay, we're going to look at that. And then we're going to see how can we extend the sampling methods we've seen, the importance sampling, for this case of estimating the posterior PDF for parameters. So far, in all the cases we've looked at together, we've employed the data to estimate our posterior knowledge given the hypothesis that x hat was a true quantity, okay? It was deterministic. So in that case, this was our posterior. And we've seen that as the number of independent observations increase, since x is a deterministic true quantity that exists in real life, as the more and more data is collected, our posterior is going to shrink and converge to the true value. So its expected value is going to be coincident with the true value, and the variance is going to tend to 0. Okay? This is what's happening when x is a true quantity that exists in real life. When this is not true, when x hat is not a deterministic quantity, but x is instead of a random variable, then this is a different behavior that we're going to obtain. Take, for example, the problem where we're trying to model the strength of concrete. Okay, concrete is something that has intrinsic variability. Okay, if I take two samples from the same concrete batch from the same mix and I test their resistance in a press, I'm going to obtain two different results. Okay, just because of the heterogeneity of all that concrete and aggregate matrix. Okay, so we can consider the strength of concrete as a random variable. Okay, and what I want to do here is to use several concrete samples in order to characterize what are going to be the parameter of the PDF, describing that intrinsic variability associated with the strength of concrete. Okay. So here x is a random variable described by a PDF, which is going to be parameterized by theta. So for instance, if f would be normal, theta would be its mean, expected value, and variance. So theta are the parameters of that PDF. X are going to be realization of my phenomena. So here is going to be, for instance, several concrete samples. And what I'm trying to obtain is that posterior, okay? The posterior probability for theta, which is the likelihood of my observation given the values of theta, times my prior probability for the values of theta divided by normalization constant. So here, given that x is a random variable, this is the strength of my concrete, which is characterized by this PDF. But here the issue here is that I don't know what are the parameters of that PDF. I don't know what's the mean resistance and the standard deviation of that resistance for my concrete. And this is what I'm trying to characterize. So what I need to do, I need to define what is my prior knowledge, not for the resistance of concrete, but what is my prior knowledge for the parameter describing the PDF of my concrete. This is what I represented here. And actually, what we're going to realize is that prior, and especially the posterior here, doesn't have to be independent, okay? It is, in most cases, dependent. So we have to represent the joint posterior knowledge of my parameter mu and sigma as a function of the samples I will collect. So this represents my posterior knowledge for what the parameter of the distribution for my concrete resistance could be. So in practice, I don't have a single true value for x. X is intrinsically random, described by this distribution. Where there's a true value is for what are the parameter of that distribution, describing, say, the expected value and the variance. And as I'm going to increase the number of observations, that surface representing my posterior for the parameter mu x and sigma x is going to shrink and is going to converge to the true value. Okay, we're going to explore that step by step. So in terms of notation, x are realization from the random variable capital X, which can be represented as being implicitly or explicitly dependent on some parameter thetas. Okay, so thetas are realization from the same random variable, which is described by this prior f of theta. So f of d given theta is going to be my likelihood of my observation from y1 to yd, given the parameter value theta can take. And at the end goal I'm trying to achieve is to obtain f of theta given d, the posterior PDF for my unknown parameters. And another new concept we're going to introduce is what we call the posterior predictive. Okay, here I have the posterior PDF for my unknown parameter, but this is not really what I'm interested in. What I'm interested in is what is going to be the resulting distribution, describing not the PDF for the parameter, but for the resistance of my concrete. So how do we obtain this? By looking at this conditional PDF. So remember, having the semicolon or having the vertical bar for the condition, it's the same thing in practice. Okay, both represent a conditional relation. So in that case, I can build my joint for both X, my concrete resistance, and the parameter or its PDF by taking the product of these two. And if I integrate with respect to d theta, I'm going to marginalize the effect of theta. And the result, the outcome, is going to be the posterior predictive PDF for the random variable of interest, in this case, X. Okay, now let's look more closely at the prior f of theta. So f of theta describe our prior knowledge for the value that theta can take. Okay, as it was the case before, the prior knowledge can be based either on engineering heuristics, in the case of sequential data analysis, like in the case of the fire example we'll look at earlier, could be the posterior PDF obtained from previous data, or it could be non-informative prior. Okay, in this case, absence of prior knowledge. But here, keep in mind, non-informative prior is not necessarily equal to uniform prior. Okay, in the case of the mean value, which is unbounded from minus infinity to plus infinity, it is the case. So we can say that my prior knowledge for the mean is proportional to 1, so uniform. But in the case of standard deviation, what's going to be considered as a non-informative prior is going to be 1 over sigma. Okay, in that case, it reflects our knowledge that all order of magnitudes for any value of sigma are equally probable. Okay, but here in both cases, we have proportional to 1 over sigma. Why? Because these are improper probability density function. You cannot have a uniform distribution over an infinite range that's going to integrate to 1, okay? So it doesn't integrate to 1. It's not going to be a proper PDF. So in such a case, you cannot sample from a non-informative prior, okay? Because it's not a proper probability distribution. So in that case, the integral of f of mu, for instance, is going to be equal to infinity, which is not equal to 1. So in that case, if you want to take samples in this case, you will have to rely on the methods we're going to see in Module 4 using MCMC, Markov chain, Monte Carlo. Okay, the likelihood, we can write it either as f of d given theta. This is the most common form we're going to use. But analogously, what we want to say is what is the probability density that the outcome of my random variable y are specific instance lowercase y, given values of theta. This is f of y given theta, so we can just ditch here the representation of the random variable. Or inversely, some references are going to say, I'm going to reverse the order, but it means the same thing. The likelihood of observing y given values of theta, okay? So given a set of observation D that contain a single observation y1, which is a realization of that additive observation process, okay? Where V is my observation process error, and X represent the probability density for the phenomenon X I'm trying to characterize. So X is intrinsically a random variable, but what I don't know here is what is its expected value and what is its variance, okay? Here, these are going to be my two parameters, mu X and sigma X. So my likelihood, what is the likelihood of observing Y given specific value for mu X and sigma X, is going to be described here through that additive observation process by the sum of X plus V, where X is normal and V is normal, okay? If I assume that X and V are statistically independent, my expected value is going to be the sum of the mean, so mu X plus 0, mu X. And the variance here is, if we have the independence, the assumption of independence is going to be the variance of x plus the variance of v. So sigma x squared plus sigma v squared. So if instead of having an additive observation process, I would have a multiplicative observation process. Okay, typically what we're going to do to maintain the analytical correctability, I'm going to assume that v is log normal and x is log normal. So in this case, if you look at what we've seen in the module 2, when we review the log normal probability, is that the product of log normal PDFs still lead to log normal PDF. In that case would mean mu ln of x in the log space, and I'm going to sum the variance in the log space as well as the variance for my likelihood. Okay, so what's the effect of the amount of data available on my posterior? Okay, we saw in the previous module that as my amount of independent data would tend to infinity, if x is a deterministic quantity, my posterior will converge to a Dirac, so all the probability content concentrated on a single value corresponding to the ground truth. In the case here where x is a random variable, there's no ground truth for x. X is intrinsically described by a probability density function. So in that case, as the number of independent data tends to infinity, my posterior is going to tend to a Dirac delta, but my posterior is for parameter, not the values of x, not for the strength of concrete, but for the parameter describing the PDF for the strength of concrete. Okay, so what converts to Dirac delta here is my posterior for the parameter of my PDF. So same thing, the expected value will tend to the true value. The variance for my parameter tends to 0. Now, what is the link between this and what we defined earlier as the posterior predictive? Okay, using Bayes, I can define my posterior for theta given my observation. Okay, by the product of the likelihood times the prior divided by my normalization constant. Okay, so here what we're going to be seeking is to quantify the posterior predictive. Okay, how much or knowledge of theta affects our knowledge for x. Okay, so I'm learning through Bayes this quantity, and I want to know what is the impact of that imperfect knowledge for theta on x. And to do this, I'll take the product of my conditional probability of x given theta times the posterior I have here. So the product of these two is going to be the join for x and theta, and then I marginalize by integrating over possible values of theta. Okay. So now we're going to look, how can we use Monte Carlo sampling to do the same operation we were doing before, but this time in case where x is a random variable. So we're trying to quantify the posterior for the parameter of the PDF of that random variable. So if we take our samples in our prior, it means that our normalization constant can be approximated by 1 over s, the sum over my sample of the product for all my observations. So what's inside of the bracket here is going to be my joint likelihood for my set of d observation, where these are my marginal likelihood. So what is the probability density of observing the observation yj given the sample value of theta s? I can do the same thing for the expected value, where now my normalization constant is going to be approximated by what my approximation here, and same thing for my variance, where I simply replace theta s by theta minus the expected value approximated here to the power 2. Okay, now the step that differs a little bit is how can I approximate my posterior predictive PDF? Okay, so again, I'm going to take samples theta from my prior distribution for the parameter, the PDF of theta. Okay, so xs, our realization, I take my samples from theta s from my prior distribution for theta. But now I need to take another set of samples, okay? I need to take samples from x, okay? But this sample from x depends on the parameter. So what I do is that for any sample xs I want to obtain, I take the same corresponding sample xs, theta s, that comes from the parameter, okay? I take a sample from that PDF, that takes themselves the realization from my prior here, okay? So in that case, by doing the same mechanics again. So I will be able to characterize what is my expected value for my posterior predictive for x given my data by 1 over s, the sum over all my sample of my xs, my sample taking here from my distribution for x, which themselves depends on my sample for thetas, okay? Times the likelihood of y given theta s divided by my evidence, my normalization constant. Same thing for my variance, except that I replace xs by xs minus the expected value estimated here. Okay, let's apply this. We're going to apply this to the concrete strength characterization, where the strength of the concrete is going to be represented by the random variable r, okay, which has an intrinsic strength, okay, or intrinsic value. No, the strength has an intrinsic variability, and this variability is characterized by the probability distribution function for the resistance. And here, this is a synthetic example, okay? I create this example, so I know what are the true value. So the true value for that PDF are, the expected value is 42 megapascal, and standard deviation is 2 megapascal, 2 MPa. Okay? I know these values because I generate synthetic data, but actually, during the treatment of the problem, never we have access to these true values, okay? We're gonna see if, as I increase my number of concrete samples, my posterior is gonna tend toward these true values, okay? So we're gonna say that my strength, R, is gonna be distributed like a log normal because I want to restrict it to, say, positive value. Describing the strength R. And this is characterized by the mean of the resistance in the log transform space, its standard deviation. And we've seen from what we saw in the probability distribution module in module 3 that there's a 1-to-1 relationship between mu r and sigma r, so the mean and standard deviation, 42 and 2, and the parameter in the log transform space. So the posterior I want to obtain is the posterior for mu r and sigma r, these two quantities, okay? I want to know, as I increase the number of sample, how my knowledge concentrate towards these true values. To do this, I need to define my likelihood for my set of observation for the strength of each sample, times my prior knowledge for these two parameters, divided by my evidence, my normalization constant, okay? So here we assume that mu r and sigma r, my prior knowledge for these two is statistically independent, so that I can build my joint prior knowledge by the product of the marginal, where each marginal, we're going to assume it's log normal, with the prior mean for mu r is 45, and the prior variance, the prior standard deviation for mu r is 7 megapascal, okay? So this is the mean for mu r, this is the standard deviation for mu r. The mean for sigma r is 5 MPa. The standard deviation for sigma r are 2 megapascal, okay? So theoretically, mu r and sigma r would be called parameters. Mu of mu r, sigma of mu r, mu of sigma r, and sigma of sigma r, these would be called hyperparameters, okay? Parameters of my prior knowledge. So if we assume that my observation errors are obtained through either the multiplicative process or the log transform additive process, these two are equivalent, where V is my observation error, which is normal with mean 0, variance 0.01 squared. Okay, and here this is a direct observation because I assume that the capacity of my press is greater than the strength of my sample, meaning that I'm really going to be able to crush my concrete sample and obtain what was this resistance, okay? So the likelihood here for my observation, y given theta, is going to be a log normal with mean mu of ln of r, because I knew that my resistance for my concrete as mean mu r, or mu of ln of r, and a variance sigma of ln of r, okay? Because this is the mean and variance in the log transform space. So since my observation error is defined here in the log transform space as well, I can simply add here the mean here, which is 0, and I had the variance here, which is sigma v squared. So my joint log likelihood for a set of D concrete core is going to be the product over each of my sample of the log normal distribution here, where yi, or log of y high, is going to be the actual value recorded by my concrete press that crushed my concrete cylinder. Okay. So if we look at the result, here we assume that the first concrete sample we break with a strength of 39.7 megapascal. Okay. What we represent here with this surface is going to be my prior PDF for mu r and sigma r. Okay, this was my prior knowledge. The red dots represent the reality. Okay, I don't have access to the reality. I want to put it here just to compare our knowledge to the ground truth here. So this is my likelihood, the likelihood of observing the strength of a cylinder given the value of mu r and sigma r. This is my likelihood for one cylinder, okay? And if I take the product point to point of these two things and I normalize using my evidence, I'm going to name my posterior here. So this is my posterior knowledge for what could be mu r and sigma r, given my observation of the concrete cylinder strength, as well as my prior knowledge. So you see, that was my prior. This is my posterior. It's a lot more compact, and it's not yet very concentrated around the true value, but I have only broke one concrete sample. And what you see here is the posterior predictive. So if I draw the posterior or the PDF, knowing the true value that I know because this is synthetic data, it would be the blue curve you see here. Okay, and now my posterior predictive for what could be the resistance or the variability in the resistance of concrete is the red curve you see here. You see, it's much broader than the reality because I still have a lot of uncertainty in the posterior for my parameters. Okay, so you see how we go from the prior, which is diffuse. This is my likelihood. It concentrates a little more my information for my posterior. Now, what if instead of having a single observation, I have two concrete observations, so two strength observations. So my prior remains the same thing. My likelihood gets a little sharper, and you see that it concentrates over my posterior a little more toward the real data. It's not fully concentrated on the real data, but it's a little more compact towards it. And if you look at the posterior predictive, it shifted it a bit and makes it a little more concentrated. What if instead of having two observations, I'm going to have 5? So now my likelihood is a lot more concentrated. My posterior is a lot more concentrated, okay? It's not yet a direct. It's not all the way on the true value, but now we see that the value is highly likely, okay? And you see, going from here, this is for 2 observations. With 5, my posterior predictive gets really close to the reality. If I have 10 observations, my likelihood gets really peak. My posterior gets really peak as well. If I would use 100 concrete sample, we can look at the posterior, okay? It's not a direct, but it's really, really close to it. And the result is that my posterior predictive is going to be almost coincident with the reality, okay? So that's how we can use Bayes' rule in the context where you have few data points to really extract all the information there is from your observations. Okay? One issue with everything we see right now is that Bayesian estimation is intrinsically, or at least in many cases, computationally expensive. Okay? That's why, we're going to see later on, we cannot, even if we can frame the problem using Bayesian estimation, we cannot always exactly solve using Bayesian estimation because it can be computationally prohibitive. Okay? In some cases, although, we might have some really quick shortcut. Oh, before seeing this, give me a second. As the number of data tends to infinity, so in this case, even with 100, we saw that the posterior here tends to a direct, all concentrated on the true value. Okay, meaning that the expected value tends to the true value for the parameters, and the PDF or the resistance tends to the true PDF, okay? Now, as I was saying, in some special Bayesian updating or Bayesian estimation is intrinsically complex and can be intrinsically computationally demanding, okay? But in some special cases, we have some instant shortcut to do analytically tractable Bayesian inference or Bayesian estimation. And this is the case for what we call conjugate prior. Okay, we're going to see in more detail. What is it? What is the mathematical formulation? And we're going to look at an applied example of conjugate prior. Okay, by definition, what's a conjugate prior? It's specific combination of prior distribution and likelihood function so that the result is that the posterior is going to follow the same family distribution as the prior PDF. Okay, so if the prior and likelihood have specific type, the prior and the posterior are going to be the same family type. And not only we're going to have the same family type, there's going to be analytically tractable formulation to do that Bayesian estimation in order to obtain the closed form solution for what are going to be my posterior parameter values. So that makes it instant result without having to resort to sampling methods, to integration, to anything. Okay, this is Bayesian estimation that is analytically tractable. So in module 3, when we look at the beta distribution, okay, we saw that we could use the beta distribution in order to characterize what is the probability of a thumbtack heading on either head like this or tail like this. Okay, because we saw that we're going to model X as being the probability, say, of head as a beta distribution. Because we say that the beta distribution is going to model a random variable that is defined in the range from 0 to 1, corresponding to the probability here. Okay, we're going to review this example and we're going to see that we could interpret the parameter of that beta PDF, which are the alpha and the beta, as pseudo counts, okay, which are the alpha would be the number of instances where we have obtained a thumbtack landing on head, and beta would be the number of outcome where the thumbtack would landed on tail, okay? And we're going to rebuild this example, and this was possible because actually the beta distribution is a conjugate prior, okay? That's why what we were doing actually earlier was applying a conjugate prior to perform Bayesian estimation, okay? So before going there, we have to ask ourselves the question, how do we define the likelihood of having 3 thumbtack like this? So first observation is head, second is tail, third is head, okay? What is the likelihood of having these 3 observations given that I know that X is probability of head, okay? The answer is going to be the product of X times tail is 1 minus X because it's the complement of the probability of head. So X times 1 minus X times X. Okay, this is how we would define the likelihood of observing these 3 observations because we know that the probability of head is X. So all of this is going to be explored in the context of what we call the beta binomial conjugate prior. Okay, so we know that if the prior is beta and the likelihood is binomial, the posterior is still going to be beta. Okay, so if we start, then we assume that in the previous context, the prior follow a beta PDF, meaning my prior knowledge of the thumbtack, be it on either head or tail, follow a beta distribution with parameters alpha and beta and given by this formulation. Okay. The likelihood of having DO or D0 observation 0, which could be, for instance, tail, and D1 observation, which would be 1, corresponding to head. We assume that these observations, or the likelihood of obtaining these observations, is going to follow a binomial distribution. Okay, as we saw before, we say that the probability of having head, tail, and head is going to be X times 1 minus X times X. If we want to generalize this to any number, it's going to be X, so the probability of head, times the number of observation of head, times 1 minus X times the number of observation of tail, okay? Where D1 is going to be the instances for observing one outcome. D0 is going to be the number of instances for observing the other outcome. So in that case, if the prior is beta, the likelihood is binomial, the posterior is going to follow a beta PDF. Because here we have the likelihood times the prior, and what we can see is that we can combine both so that the prior, or the numerator, becomes x to the alpha minus 1 plus d1, and 1 minus x to the power beta minus 1 plus d0, okay? And on the denominator, the normalization constant, which is the beta function, we simply increment, or we simply sum alpha, which was controlling our prior, plus the number of observation d1, plus, and on the other side, the second parameter is going to be beta plus d0, okay? So this allows us to make instant Bayesian updating. That's going to be scalable to really large problems, okay? So at the end, our posterior describing the probability of, in this case, ed, given the data we observed, is described by a beta distribution, which with parameter alpha plus d1 and beta plus d0. Number of ed, number of tail, and alpha and beta are prior knowledge for what was the probability of ed. Okay, let's apply this to an example of traffic safety. Okay, given we have an intersection where we know that the number of cyclists is 3 to the power times 10 to the power 5, so 300,000 cyclists a year that cross this intersection. Okay, and we know that over the course of the last 5 years, there has been 20 accidents at this intersection, such that the city decided to intervene, modify the intersection to make it safer, okay? Following those modifications to decrease the probability of accident pi old. So pi is going to be describing here the probability of accident before the modification made by the city, okay? In the period of 1 year, we only observe one accident, okay? We want to combine all the information available in that problem in order to quantify two things. What was the probability of accident before the intervention and after the intervention? And here, keep in mind, the probability of accident is not only the number of passages, so 300,000 per year times 5 years. This is the total number of people that cross this. And we don't do only 20 accidents over the number of users, okay? If we do this, we're going to completely neglect the uncertainty we have due to the fact that we have limited amount of data. Highly likely that if instead of observing 5 years of data, we would observe 20 years of data, okay? We wouldn't have the same estimate because with 20 years of data, we're going to have more data to have a better, more accurate estimate, okay? So here we want to use conjugate prior to obtain that estimate. Then we say that following the modification to decrease the probability of accident, we want to know, despite the fact that we have only 1 year of data available, how observing a single accident over the course of 1 year, so 300,000 passages, what is my new probability of accident? So in here, what's going to happen is that my prior or my posterior knowledge before modification is going to become an upper bound observation for my probability of accident after the observations, okay? So at the end, we want to use this to quantify what is going to be the predictive probability of accident, pi nu, after modification, okay? So my probability density for pi, my probability of accident, given the data I have observed before modification, is going to be a beta distribution, okay? Where my number of occurrence for accident is going to be 20, and my total number of non-occurrence is going to be 5 years times 300,000 passages a year, okay? My posterior PDF, so this is directly a conjugate PDF, because I can directly use, as it was the case in the Tomtac, my number of occurrence 20 over the total number of non-occurrence, okay? In the case of my new data, okay, what I have is here, my prior, okay, is going to be what I have here as my beta function that is not normalized, okay? This is going to be the equivalent of my likelihood, okay? I'm going to have a probability pi that I calculated earlier, time to the power, my likelihood is going to be here pi, my probability of accident, to the power 1, because I have here one accident. So I said that I had one accident over the course of 1 year, and I had 300,000 cyclists that use the intersection. So the probability of no accident is 1 minus pi to the power 300,000, okay? And this is my likelihood. My prior is 1 minus the CDF of my posterior that I have obtained using the old data. Why? Because this is an upper bound observation. I know that because the intersection was made safer, no matter what was the prior probability of accident, it's now lower than it was before. Okay? So if we try to plot this, I have on the x-axis the probability of accident, and the vertical axis is the probability of the probability density of pi, so the PDF for the probability of accident, given the data. This is before the intervention, after the intervention. So here, if we plot, we don't see anything. Why? Because the probability of accident is so small that I cannot represent it. If I want to represent it accurately, I should transform this into the log 10 space, okay? How do I transform in log 10 space? Using the change of variable rules that we cover in the revision module 1b. So in that case, my transformation function is going to be log 10. And if I apply my change of variable rules, I can obtain my PDF in the log 10 transform space as the probability in the original space times pi times log 10. So in the log 10 transform space, my probability of accident will look like this. So this is my posterior PDF before intervention. That would be my posterior PDF after intervention, okay? So here is the same plots. So here what you can see with the red line would be the posterior predictive probability of accident. So it corresponds to the expected value of that posterior PDF. So in that case, it's going to be equal to 1.38 to the power minus 5. This is my probability of accident, whereas here, after intervention, is going to be 1.20, so slightly smaller, okay? And here, in terms, this was the posterior PDF before the accident, but as we try to obtain information for the posterior after the interventions, that posterior is used as an upper bound observations in order to compute my prior for that PDF, okay? So the beta binomial is not the only one example of conjugate prior. There are several of them. So for instance, it could be the beta binomial. You have the Poisson gamma, normal, inverse gamma. There are many of them, okay? The most exhaustive list would be available on Wikipedia, where you have all the detailed formulation for each of these conjugate prior. Okay, so if we summarize what we've seen together, so in Bayes' rule, there are 4 components. What we're looking for is the posterior, okay? My PDF for the quantity of interest given the data. This is obtained by the product of the likelihood times the prior divided by my normalization constant or evidence, okay? My prior can be based either on engineering heuristics, my previous posterior PDF in the case of recurrent Bayesian estimation, or of non-informative prior. Keep in mind here, uniform and non-informative prior are not always the same thing. My likelihood, you can read this as the likelihood of my data given some values of x or some parameter value theta, is going to be the conditional probability for a set of observation given the value that x or theta can take. My evidence acts as a normalization constant. This is going to be the integral of what I have on the numerator of my Bayes rule. the evidence is typically really hard to calculate because it involves that integral, okay? The first methods we've seen here to perform that integral is using importance sampling, okay? A Monte Carlo sampling method where we can calculate our evidence or expected value for our posterior or variance for our posterior, okay? This is gonna work well, but keep in mind if we're doing importance sampling and we're sampling from our prior knowledge, it might happen that when we have a lot of data, our posterior is really concentrated around some values, okay? And sampling from the prior is gonna waste a lot of samples in part of the domain that are not relevant for us, okay? So we're gonna overcome these limitations in the next module 4, where we're gonna look at MCFC, Markov Chain Monte Carlo, okay? Which are gonna be way more applicable in practice. So this is limited to simple case. We're gonna overcome these limitations in module 4. So what we're looking for when you're doing Bayesian estimation or Bayesian inference is to characterize that posterior knowledge, okay? And what happened as the number of data increase, so as d tends to infinity, fx is a deterministic quantity, okay? I'm trying to quantify the posterior for a deterministic quantity. It means that my posterior is going to converge to a Dirac delta, meaning its expected value for my posterior is going to converge to the true value. The variance is going to shrink to 0. Keep in mind, this is if I'm dealing with identifiable problem, okay? If it's not identifiable, in 2D, it will look like a ridge of containing an infinitely many possible combination of my variable that are equally likely to explain the data I have observed. In the case where I'm trying to use Bayesian estimation to characterize my posterior for the parameter of a PDF, so this is what we're going to be using when we're going to build our machine learning models in the next module. In that case, in the presence of an infinite amount of independent data, my posterior converges to a Dirac, but my posterior for my parameters, okay? Not for the quantity of interest, which are the outcome of the PDF for, no, I'm going to rephrase it. So in the case of X is a deterministic quantity, my posterior is going to directly quantify that quantity, okay? When X is a random variable, it means that my posterior is going to quantify the posterior PDF for the parameters of that random variable, okay? So at the end, the Dirac delta is obtained for the posterior PDF for my parameters, not for the random variable X, okay? So at the end, the posterior predictive, what is it? We obtain the joint for both X, the outcome of the random variable, and theta, the parameter value characterizing its PDF. And then we marginalize thetas from that joint PDF, okay? So going from X, which could be something that is intrinsically variable, we want to characterize what are going to be the parameters, so mean and standard deviation for that parameters. So in that case, we're going to obtain the posterior PDF that characterize our current knowledge for the parameter of that quantity that is intrinsically variable, okay? All these steps can be computationally really demanding. That's why, whenever possible, you should be using conjugate prior, okay? Meaning specific combination of prior and likelihood function such that the prior and the posterior have the same family form, and for which we have analytically tractable formulation to calculate the parameter of our posterior PDF.